In our last video, we talked about the isothermal expansion of an ideal gas, and we talked about the expressions for the reversible work and the reversible heat for the process. And you might be wondering, after going through that video, like, who cares? Like, how does this have anything to do with what we're learning in this chapter? And we're about to see how all of that ties into entropy right now in this section. So earlier in the chapter, we talked about Boltzmann's equation. It says that entropy is equal to Boltzmann's constant times the natural log of the number of ways that you can arrange the molecules that are in your system. Now, we considered a system that consisted of 4 molecules, and so we could draw out the 4 molecules and we could count the number of ways that the molecules could be arranged. But what happens when you're dealing with a real life number of molecules, right? In real life, we're dealing with molar quantities, and it would be impossible for us to draw out Avogadro's number of molecules. We're not always interested in knowing what the absolute entropy of a system is. What we're interested in knowing in thermodynamics and in chemistry is what the changes in variables are going to be when we do a transformation. And so if we want to calculate what the change in entropy is, then we can use the following equation to calculate what delta S is. We're much more interested in knowing what delta S is than knowing what just S is. Delta S can be calculated by determining the reversible heat and dividing it by temperature. And if you want to see a proof of where this equation comes from and how you go from S equals KB natural log of omega to delta S equals Q reversible over T, I'll refer you to section 10.3 of the chapter from the textbook so that you can see the proof. It takes up 3 pages. It takes up a substantial amount of time to go over the proof, and I'm not testing you on the proof, so I'm not going to go over it here in these videos. What you need to know is this delta S equals Q reversible over T. And from looking at this equation, you can, for one thing, start to get a feel for what sort of units you're dealing with when you're calculating entropy, because Q is typically in units of joules, temperature is typically in units of Kelvin, and so units for entropy will typically be something like joules per Kelvin. Now this equation for delta S, Q reversible over T, is like a base equation. This equation always holds true, and from this equation you can derive a whole host of variations because different processes have different reversible heat, and so you're going to be able to derive different equations for delta S for different processes. So let's talk about that. Starting with our base equation that says the change in entropy for any process is Q reversible over T. This equation is always true. Now let's put on the restriction that we're now dealing with an isothermal expansion of an ideal gas. Previously, we came up with the expression for the reversible heat for the isothermal expansion of an ideal gas. Right, we found in our last video that Q reversible is equal to nRT times the natural log of V final over V initial. And so you could take that equation and plug it into the delta S equation. So delta S is Q reversible, nRT ln V final over V initial, divided by T. All right, well, the T's cancel out. And what we're left with is that the change in entropy for this process would be equal to nR times the natural log of V final over V initial. And this is an equation for calculating the change in entropy for any isothermal process involving an ideal gas. This would hold true regardless of whether the process actually happens reversibly or not, because delta S is a state function. So it doesn't matter if you do the process on a reversible path or on an irreversible path, the value of delta S will still be governed by this same equation, nR ln of V final over V initial. An isothermal expansion or compression of an ideal gas is not the only type of transformation that could occur. And so let's think about some other types of transformations that it can occur. They're going to have different Q reversible expressions, and so we're going to get different delta S equations for them. So again, starting with our delta S is equal to Q reversible over T, right? That equation is always true. Let's think about what would happen if we were to instead consider the vaporization of a liquid. In this case, the reversible heat is going to be something different. If you do this process at constant pressure, then heat and the change in enthalpy are the same, because remember that the change in enthalpy is defined as the constant pressure heat. And if you do a vaporization process at its normal temperature, like for instance, boiling water at 100 degrees Celsius and 1 atmosphere, then the process is considered reversible. You have, at 100 C and 1 atm, an equilibrium that exists between the liquid and the gas phases. Since you have an equilibrium between these two phases, the process is an equilibrium process, or you could say the process is a reversible process. Therefore, you would say at constant pressure, the reversible heat would be equal to the number of moles that you have of your liquid times the delta H of vaporization. And when you plug that into the delta S equation, delta S is equal to Q rev, so that's N delta H vape over T. And what temperature do you use? You should use the boiling point. So, like, if that was for water, you would put in 100 C, or you would really use it in Kelvin, so 373 Kelvin. And so TB here represents the boiling point. That's the temperature at which this process occurs. All right, let's now consider a different type of phase transition. We'll now consider melting. If you have a melting process occurring at constant pressure, again, the heat and the delta H are the same. So you would say that Q reversible would be equal to the number of moles times the delta H of fusion in this case, since we're dealing with melting. Therefore, we would get the delta S equation, N times delta H fusion over temperature, and you have to plug in the temperature that this occurs at. So that is T sub M, which represents the melting point. And I'll again say that we consider the heat of fusion to be like the reversible heat, because when you are doing the melting of a solid at its normal temperature, like for instance, ice melting at 1 atm and 0 degrees Celsius, you have equilibrium between the solid and the liquid phases. And so that's how we're able to like equate this with reversibility here. Now, we could also consider what would happen if you were to perform temperature changes on something, right? Because all of the processes that we've talked about so far have occurred at constant temperature, right? An isothermal ideal gas process is at constant temperature. And I'll remind you that I mentioned back in chapter 9 that phase transitions also always occur at constant temperature. But what happens if we do a temperature change? So for a process where the temperature changes at constant pressure, the way that you would calculate delta S would be a little bit more complicated, and you would have to do some calculus to come up with this equation. So I'm just going to say you like do some calculus, and I'm not going to do it here, but the result is what we're interested in. And the result is that you get that delta S for a process where temperature changes at constant pressure will be NCP times the natural log of T final over T initial. And lastly, you can think about what would happen if you had a temperature change that occurred at constant volume. And again, you'd have to do some calculus. So we're going to skip that part here. So we'll say you do some calculus. After doing the calculus, what you end up with is N times CV times the natural log of T final over T initial. I don't know. I kind of like doing the calculus because it's nice to actually see that the things that you learn in a calculus class can actually be used in other fields to solve like real world problems. But I recognize that that's not something required for this class. So we just saw a lot of equations. Let's take a look at a summary here. We start with the base equation delta S is equal to Q reversible over T. This equation is always true. But where you go from here depends on the process, because different processes are going to have different expressions for Q reversible. They're going to have different heats associated with them. And so from there, you can derive a whole host of variations that are specific to the type of transformation that you're doing. If you have an isothermal process involving an ideal gas, then we saw, right, Q reversible is nRT ln Vf over Vi. So that gives you delta S is nR ln Vf over Vi. If you have a process that involves melting, then the reversible heat carries a different expression to it, right? The reversible heat is the number of moles that you have times the heat of fusion. So delta S is equal to N times the heat of fusion over the melting point. If you're boiling, right, Q reversible is N times the delta H of vaporization. So delta S is N times delta H vaporization over the boiling point. If you're changing temperature at constant volume, you get delta S equals NCV ln T final over T initial. And if you do a process at constant volume, you get delta S equals NCP ln of T final over T initial. Right? There are so many different equations, and it's going to be up to you to know when to use each of these equations so that you're using the right equation to solve the problem that you're dealing with. And there are some hints that help you to figure that out, right? Like, if you see the delta S equation that has CV in it, that would be indicative of constant volume. If you see the delta S equation that contains CP in it, that is indicative of constant pressure, right? If you see delta H of fusion, right, that's telling you melting. If you see delta H vaporization, that's indicative of boiling, right? So the equations are telling you these things. And we saw an equation for constant pressure. We saw one for constant volume. And so the only other one that's remaining by like the process of elimination has to be the one that's for constant temperature, which is the isothermal ideal gas case, right? So that will allow you to very quickly identify which equations can be used at what time, so you're not wasting a lot of time looking that information up while you're taking the test. All right, that brings us to the end of this portion. This is kind of a lot to take in. We saw a lot of equations here. And what we're going to do next is go through an example